So the way when we have a function of two variables, the way we are doing it, we would integrate the y variable first, and then whatever we get will be a function of x, and we'll be integrating that. But for practical reasons, one might want to integrate x first. That might simplify the expression. That is one reason, but there is also a more deeper reason why it shouldn't matter which variable you integrate first. The order in which you integrate out the variables shouldn't matter. And that was the theorem we were trying to prove. Okay, so the statement is the following: integral f over ik doesn't depend on the choice of fj, j equal to k minus 1 all the way up to what is the last one? 1. The choice of fj. So here, I mean, the statement is somewhat vague. Choice of fj in the sense that, as I pointed out already, in the second step, when I define fk minus 1, in the first step, fk minus 1, instead of fixing the last, regarding it as a integrating it out xk, I might have integrated out any other variable as well. Then fk minus 1 would be a function of the variables which would be left after integrating out that specific variable. So, and the proof involves, so actually this is the main step in defining multivariable integrals, to show that this doesn't depend on the way we integrate, the order of integration of which variables we pick first. But Rudin's approach is not the standard one. If you look at other texts, say Apostle, or there are so many basic texts in real analysis, they don't do it this way. What they do is they just go carry over the one variable construction. In one variable, what we do is we try to put rectangles below and above the graph of the function, define upper and lower sums, and show that the function is set. You say function is integrable if the supremum and infimum of this upper and lower sums will coincide. That takes a while. I mean, but that works even in this case. That takes a while. But even if you do it that way, it won't be clear that the order of integration will not matter. Yeah, first of all, it's not clear that the integral that you get. Let me just make this remark instead of talking so much. So, remark, one usually defines integral f over ik by using upper and lower Riemann sums, as in the one variable case. In this setting, it will be a theorem that this integral is equal to an iterated integral as we have defined. So it's not that, I mean, there's no, basically there's no free pass. You, whatever way you do, the difficulty will be shifted somewhere. If you take the upper lower sum approach, then still one is left with the task of showing that that the integral one gets that way will be equal to this iterated integral. For us, the integral means an iterated integral. But if you go this Riemann sum via this Riemann sum approach or our approach, one thing has to be proved, namely the sequence of iterated integrals. It doesn't matter which order you do the integration. Okay. Actually, yeah, if you take the Riemann sum approach, that will become easier because if you show that the definition of the integral in this other approach will not involve one variable integrals at all. So if you show that this integral f is equal to one specific iterated integral, then you're shown it's any other iterated integral will also be the same thing, because that's all. Well, yeah, but the point is that no, okay, let me leave it at that. Anyway, so there is something to be said there, but the point is that if you go the Riemann sum approach, you definitely are left with the task of showing that this integral is equal to an iterated integral. That much is for sure. For us, we have defined it as an iterated integral, but there's no unique iterated integral. You can, depends on which variable you take, integrate out first and so on. So we have to see that the theorem is that it doesn't matter. So, and the idea of the proof is that the theorem is true for special, for functions. Let me not use the word special. Just say functions of the form h of x equals h1 x1 hk xk, where hi from ai to pi r is continuous, I equal to 1 to k. So for a product of one variable functions, it is true. And in fact, last time I did the k equals 2 case. The k equals 2 case, but the same thing will work for any k as well. This integral of this kind of function will turn out to be just h1 x1 dx1 product of all these intervals. Oh, actually, let me not use this. Last time I'd used this notation. What was the notation? LF. LF equals LF L prime F equals this, where LF and L prime F are two ways of performing the iterated integral construction. So now, as I said, then one looks at this, let script A be the set of all finite sums of these kinds of functions. So finite sums of products of one variable functions. Then I said that the script A, this one is an algebra, i.e. A is a vector space, algebra of functions. Vector space F times G belongs to A if F and G belong to A. Okay, so this is where we had stopped last time. Well, the crucial thing is, the other thing is that this LG equal to L prime G for any G in A. I had asked you to check this. I mean, there's not much to check. So see, we've already seen that LG equal to L prime G if G is a product of one variable functions. That's what I just said. But here, G is not quite a product of one variable functions. It's a finite sum of such things. Now, we have not abstractly stated any theorem which says that the integral, as we have defined, is additive. So integral of F plus G is integral F plus integral G, or integral of constant F is constant times integral F. These are expected things, but we have not stated that. We have not proved such things, but we can just go to the definition of LG and or L prime G and directly check that this is true, that if G is a sum of one variable, products of one variable functions, then this equation holds. So you just use additivity for each step, those Fk minus 1 or F prime K minus 1 that you get. Each one will be, you use additivity at that stage. That's it. As I said last time, all of these things that I write as check or homework during the lecture will basically make you go over the definitions and constructions. The actual mathematical, there's no trick involved or any such thing, but you have to understand construction, that's it. Now, so now we come to, what is the point of all this algebra stuff? The point is that once we have an algebra, it turns out that, of course, anything, this algebra A is contained in, I'd introduced this notation last time, C of Ik. This is the set of all continuous functions on Ik. I mean, all I'm saying is that everything in A is continuous. Okay, so because I'm just looking at products of continuous one variable continuous functions, which is continuous, then taking finite sums of such things, which will be again continuous. So there is a very powerful theorem called the Stone-Weierstrass theorem. So since I'm going to talk about this, let me just take a small deviation and anyway say something more about this. So the precursor to this is the Weierstrass theorem, which is almost 50 years or more older than the Stone-Weierstrass generalization. Let me just state it in the context of this IK. If F belongs to CIK, the IK is not important, any compact set will do. Then there exists a polynomial in K variables. Oh, if F belongs to CIK and epsilon greater than 0, then there is a polynomial in K variables P such that f of x minus p of x is less than epsilon for all x in I. So this is quite a powerful and surprising theorem. What we are saying is that any continuous function can be approximated pointwise. See, this f of x, modulus of f of x minus p of x less than epsilon holds for all x in ik minus 1. So we are saying that any continuous function can be approximated by a polynomial pointwise. So how does one do this? Well, that's a different story, but it'll be fun for you to think about how to construct such a polynomial. Given a continuous function, how would we go about getting hold of such a polynomial? Obviously, as epsilon becomes smaller, you can expect that the degree of this polynomial will become very large. That's something one can't control. But still, we get hold of a polynomial. So this theorem it can be very useful whenever suppose you are given a continuous function and you want to prove a statement. That's if it happens that that statement is obvious for a polynomial, then you try to use this theorem. You first prove you remark that it's obvious for a polynomial, then you approximate this by the given continuous function by polynomial and then try to prove the statement for the given continuous function. That is in fact the idea of how we are going to use not quite this, but its generalization. The Stone generalization of this is, so I'll just write SW theorem. Let A be an A subset CIK be an algebra. Suppose, oh, by the way, where does this algebra begin stuff come into picture? Well, you notice that if you look at the set of all polynomials, that is indeed an algebra. That is a vector space. Polynomials of yeah, the set of all polynomials is a vector space, and if you multiply two polynomials, you again get a polynomial. So it's an algebra, but just so the idea is that if instead of just working with polynomials, suppose I'm given an algebra in CIK, can I approximate a given continuous function by elements of that algebra? So it turns out that it's not enough that you just start with an algebra. You need a couple of conditions on the algebra. Suppose one. The first condition is A separates points. What does this mean? i.e., if x1 not equal to x2 are elements of this K cell. Again, the K cell is, I should emphasize, the K cell is totally irrelevant. Any compact set will do. So if x1 is not equal to x2, then there exists f in A such that f of x1 not equal to f of x2. So what it's saying is that there are sufficiently many functions inside this A so that whenever we have two distinct points, I can find a function which will whose values at those 2 points are not the same. This certainly happens for a polynomial, right? I'll leave it to you to think why it's true for this, and the next one are obvious for polynomials. If A happens to be the algebra of polynomials. The second, other thing is A vanishes at no point of IK. So what does this mean? It just means that there's no point in IK such that all the functions of in A are all 0 at that point. This condition does not follow from the first one. The two are independent conditions. So there's no point such that all of them are 0. So what that means is, another way of stating it is that, i.e., given any point, given any x in IK, there is an f in the algebra such that f of x is not equal to 0. So at every point, some function in the algebra will not be 0. So these two hypotheses are the crucial, insights which will make the Weierstrass theorem work for any algebra. So if you have these two conditions, then the same conclusion. Then given any f in CIK and epsilon greater than 0, there exists an element of the algebra such that f of x minus g of x less than epsilon for all x in I. I'm giving a lecture. So then, such that this happens. Well, okay, the statement and the conclusion is clear. Now all we have to do is let's verify. So we want this for our algebra, that we want to approximate any continuous function by an element of the algebra, and by applying the Stone-Weierstrass theorem. But so we already seen that our A is an algebra, we just have to check these two conditions, 1 and 2. So let's see that in our case, A separates points. So let's take 2 points, x1. No, let me use different notation now. X and y. X not equal to y in I. Okay. So I would like to find some g in A with g of x is not such that g of x not equal to g of y. So how would I do that? Now g of x is by definition, it has to be a sum of product of one variable functions. Okay. So I'll give you 2 minutes. So tell me how what g, how can I find a g which will separate these 2 points? Anyone?
If x is not equal to y, then we can say that they're different in
Yeah,
at least one variable. So you take a linear function in
one
that variable.
coordinate. Yeah, that's it. And what about yeah? Well, so what would your g be? I mean, how would it
Uh,
depend on the other variables?
it depend, like that's fine.
Sorry.
It can just not depend on the other variables.
Yeah, that's it. So you just if x is not equal to y, that means that xj is not equal to yj for some j. Some coordinate is not equal. Then you can just take let g of x be. Oh, actually, my notation is pretty bad. So if again this okay, here let me say g of z. Z is not a complex variable now, but it's just a element of Rk. Z be just the kth variable. So if you want to think of it as a product of functions, then the other functions. So in other words, Gj Zj equal to Zj. All the other ones, Giz Gizi equal to 1 if I is not equal to j. Okay, they are all the constant functions 1. So the product of these things will give you this g, and that will separate those 2 points. So it's the immediate. As for the second one, let's take a point x in ik. Now again, this x may not be a good idea. Let me take a p. I want g in the algebra with g of p is not equal to 0. This is yeah, this is even more obvious than the other one. So what? How would you take? How would you get hold of such a g?
You
Hmm?
can take a
Just take the
constant
constant
function.
function.
Just take a constant function. So both are trivially satisfied, so we can apply the Stone-Weierstrass theorem. So as I said, this is kind of cheating because we are not working from basic principles. We are quoting a big theorem, which is always to be avoided as far as possible. When you're writing a proof, you would want to make it self-contained. But in the Rudin's exposition, it makes sense because it's part of the same text. So he assumes that people have gone over that already. So here we are just using it, just pulling it out of the previous chapters and using it. All right. So therefore, given f in ik, Cik, and epsilon greater than 0, there exists G in A with f of x minus g of x less than epsilon for all x in ik. Well, from this, we want to conclude. Now, our main interest is those iterated integrals, which we have not mentioned at all so far. So now let's look at those. So LF first, let me here, instead of ultimately, I want to are close by epsilon, and since epsilon is arbitrary, we'll see that they are actually equal. But to get the same epsilon, let me use this V. I'll throw in a constant V, where V is intuitively it's a volume of the cube, volume of the K cell. But since we have not defined volume, let's just say what it is. Numerically, it is just B1 minus A1 BK minus AK. Basically, the lengths of all those intervals which make up the cube, which make up the K cell, you multiply them and you get V. And then you stick in this, so you start with some epsilon, but you use a different epsilon by V in the Stone-Weierstrass theorem. So you get this. Now, first thing is that, note, first claim is that L of f minus g less than epsilon and L prime of f minus g, both are less than epsilon. So this again is quite straightforward from the definition. So I'll ask you to check a slightly more general fact. I mean, it's not all that more general. If H belongs to C of ik and modulus of H of x is less than epsilon over V for all x, then LH L of H less than epsilon, L prime H less than epsilon. So obviously in our case, this H is just F minus G. We already know that F minus G modular this for F minus G, this condition holds. F of x minus G of x less than, so that's what this H is. And so that's a hypothesis here. And the conclusion is that if this happens, then the integrals are both small. And the way you check it is the same old thing. I mean, just there's not much you can use at this stage. We have not proved anything. So you just have to go back to the definition. That's it. So ultimately, it will boil down to this fact. If you have two functions, one variable functions, such that f of x, modulus of f of x minus g of x is less than epsilon, then their integrals are also, modulus of the difference between the integrals is also less than epsilon. So using this, so you have to check this, and then now we are almost done. Since L of f minus L of, I want to say that this difference is very small. So I'll just write it as, use triangle inequality and say this is less than or equal to L of f minus L of g plus, I throw in this L of g, sorry, minus L prime f. But now notice that L of g is the same as L prime g, because g was in the algebra. That is the main part actually, that for the whole point of bringing in the algebra was that for those things, L and L prime coincide. This happens. Then that's the same as, oh, by the way, here I was saying just a few minutes ago that the linearity of the integral has not been proved, etc. Now, when I use this notation L of f minus g, notice that here I've written L of f minus L of g. I've not written L of f minus g. But again, using the iterated integral construction, this is quite easy to see that this and this are the same. But I really don't need this actually. Do I need this? Yeah, no, I do need it actually. Yeah, because so this is L of f minus g plus L prime g minus f, this. So again, I will mention this remark. It follows from the definition that L and L prime are linear, i.e. L of f plus g is Lf plus Lg. L of constant times f is constant times L of f for any constant. And the similar statement for L prime. So again, this is one of the advantages of this Rudin's approach, that these statements become quite immediate. If you work with Riemann sums, even in the one variable case, it's not difficult, but you have to again go through the upper sums, lower sums to prove these statements. Here we have just invoke the one variable linearity and get it immediately. So I won't prove this. I mean, there's no, if yeah. So that has been used in the last step here, that L of F, this is. Now, to complete the proof, we already see that L of F minus G is less than epsilon because of this check business. And so the whole thing will be 2 epsilon. So you end up concluding that L of F minus L prime F less than 2 epsilon for any epsilon. So this implies L of F equal to L prime F. Okay, so that completes the proof of this, that changing the order will not matter. At least, I mean, we are still sticking with just continuous functions, by the way. We have not talked about what is a class of Riemann integrable functions in multivariables. That issue doesn't even arise here. We just started with a continuous function and then went on doing this. That is another drawback of this process, Rudin's process, compared to the Riemann sum approach, that we are necessarily restricting, because if you look at the construction, we actually use the fact that we have a continuous function. This fk minus 1 is, and so on. So, but still sticking with in the realm of continuous functions. Now let's see. I'll end with this thing. So we want to now define integral f over whole of Rk, where f has, this is a very important and frequently occurring in analysis, especially if you study harmonic analysis or any kind of analysis, PDE, partial differential equations, and so on, you'll see this thing, compact support often, where f has compact support. What does this mean? So f definition, if f is a function on Rk, R, the support of f is the set. Rudin doesn't use this notation support like this, but I'll just introduce this. Support of f is defined to be, you look at the set of all x such that f of x is not equal to 0. And then you take the closure of that set. Closure of the set of points where f is not 0. This makes sense for any function. I don't even need continuity. I'm not saying anything about this set. I just look at points where it's not 0. Then for any set, we can take the closure. And that's what I do. So I get this. Notice that if f is continuous, the set of all x such that f of x is not equal to 0, what kind of set will this be before taking the closure? this set of x such that f of x is not equal to 0 when f is continuous. Anyone? Set of x such that f of x is not equal to 0. Can we say anything about this set?
It's open.
Yeah, it will be an open subset of Rk. Why? Just that if f of x is not equal to 0 at a point, in a small ball around that, it will not be 0 by continuity. That's it. Or you can also see that this is the inverse image of minus infinity 0 union 0 infinity. Inverse image of this. Now this thing is R minus 0, which is an open set. So inverse image of an open set is open if f is continuous. But this is not the support. The support will be the closure of this. But so we are going to look at if f is a continuous function on Rk with compact support, we define integral of f over Rk to be integral of f over some k cell where Ik is a k cell with such that Ik contains support of f. So the picture is like this. The support of f, this is the support of f. It's some complicated set. It's a closure of an open set. I just I put it inside some k cell, Ik. Then I look at integral of f over Ik and call. Obviously, if I want to do this, the first thing is that there should be no choice involved. So I can put this compact set in many different, I can put it in a different k cell as well, Jk. So the claim is that integral of f over Ik equal to integral of f over Jk. It doesn't matter which thing you use. And again, so this definition is, I can be sort of casual about saying a K cell such that which contains a support. I really don't have to worry about which one. And why this is true? Well, this is the only way to prove such things is you have to go by definition. So you just use the iterated integral. And now we have a freedom in using whatever iterated integral we want. And one can see that this is true. So what I'll do is, since from 23rd to 27th, there won't be any classes. So 2 classes will be gone by then. I'll think about it and maybe post one more lecture, because one more lecture and some maybe an example. But I don't want to do too much, because all the remaining stuff is kind of it's very important. Anyway, yeah, I might post it. I don't know, because see, even when I during my lectures, anyway, you don't ask. Typically, there aren't any questions. So there should be no difference between a posted lecture and a live lecture, right? Some of you said that you prefer live lectures, but in practice, it's not that you have any questions or you're stopping me. So let me see how it goes. I might post a couple of lectures, but in the next time we meet, I'll devote some time to answering any doubts about that, whatever lecture I would have posted. So shall we end today's lecture?
Okay, sir.
Yeah. Okay. Thank you.
Thank you, sir.
Thank you, sir.
Okay.